All right, good afternoon. So I'm going to talk about pressure relief valves and their interaction with governor upgrades. Just to start off, because pressure relief valves aren't incredibly common. Who here either has one at their plant or has worked with one? So there's a small handful of hands, but enough here. Feel free to ask questions and chime in at the end. So I'm going to talk about pressure relief valves and what they do, how they interact with governors, and then give a few examples of different types of configurations and how they may be affected or not affected by a governor conversion. So pressure relief valves are a Penstock safety device that are installed on Francis units. On a typical Francis unit, the Penstock pressure rise during a load rejection is controlled by the rate of gate closure. The gates will close at a rate that is slow enough to prevent water hammer in the Penstock, but fast enough to prevent excessive overspeed on a load rejection. On some high head units, that balance cannot be struck, and an alternate means to relieve pressure in the Penstock is needed, and that is normally done through a pressure relief valve. There are other means, but that's a quite common means. Alternately, or additionally, PRVs are sometimes used as a bypass valve to maintain downstream flow in critical applications, fish flows, irrigation flows, recreational flows, and such. So in the photo here, just to show how this is tied in, the Penstock is coming in on the left-hand side of the spiral case and going through the turbine. Down at the bottom right-hand side, you have a valve that is normally closed, but on a load rejection or a fast gate closure of any sort will open to maintain control the flow of water through the turbine and the subsequent pressure rise. So what you see here is a few lines. The blue line on the top is Penstock pressure. I'm going to slide forward. I'm going to zoom in on this. So the green line on the left is the wicket gate position, closing from about 75% gate down. The red line is the PRV position, and then the yellow line, which is overlapping the red line for much of this, is the total flow through the Penstock entire system. And what you see happening is there's a handoff. As the gates close fast, the PRV opens and allows the wicket gates to choke off or close off flow through the turbine and shut the unit down. But the Penstock doesn't see that fast reduction in flow. So here we're zoomed in a little bit. You can see a little bit closer what's going on. We had this was some testing from just a few weeks ago. You have a 86 trip, 86E trip resulting in load rejection. The gates close, the green line, the PRV opens, the red line. There is a little bit of a time delay there, usually on the order of less than half a second, but depending on the type of system, that time can range from tenths of a second to about half a second. And during that initial drop in total flow, the yellow line, you can see the subsequent rise in the blue line and the Penstock pressure. But then once the system is kind of caught up, just to go back, you can see that the PRV will open quickly to transition flow from the wicket gates to the PRV, and then will close slowly to slowly close up the flow in a much controlled way. And you can see just during that transition, you get a small pressure rise. So that's what PRVs do. What does a governor conversion have to do with a PRV? Usually nothing. In most cases, the PRV is operated by the servomotor or by the shift ring and is relatively independent. And other than recognizing that, there's not much that needs to be looked at. Sometimes it has a little bit to do with it. We'll look at an example where the PRV is operated off of an intermediate component of the governor, or somehow tied in with the governor in a way where it's relatively disconnected, but they can still have some influence on each other. And then, and very rarely though, they are completely intertwined with each other. And we'll look at one of those cases. So this is an example of a plant in California. It's a Baldwin Lima Hamilton or Pelton PRV controller. It's probably the most traditional arrangement. I apologize for the poor angle of the photo, but you can see, I don't know if I have a mouse or a pointer there. You can see coming off the rear end of the cylinder is a connecting link that is operating to the PRV dash pod and is providing a wicket gate position. So as that PRV closes, as that wicket gates close quickly, through a dash pod. If the gates close faster than the dash pod can absorb, the PRV will operate. This really has no interconnection with the governor, is completely isolated. We sometimes might put a position indication on for monitoring purposes, but really has no impact. Another example, also in California, this is a system by Gouverneur, is less common. It's a hydraulic plate. This might be a little bit hard to follow. If anyone's interested, you can grab me afterwards. I can go through it in a little more detail. But you have a double-chambered hydraulic cylinders or servomotors. And what's happening is as the servomotors are closing quickly, that second chamber is sending oil, this purple line, up to the PRV. And if that oil is moving faster than the series of orifices and check valves and whatnot can absorb, then that will cause the PRV to operate. Also not directly tied into the controls, but what you can see here is if the PRV would ever be manually operated, that oil can also flow back into the cylinder. So they are tied together in some manner. If you do manual PRV testing where through the selection of valves at the top, you're going to dry stroke the PRV, you will see the gates operate because of that. Additionally, you have all sorts of more complicated than usual arrangements with the double acting cylinder because they're larger than they need to be. You have a force limiting cylinder attached to the end of it. So it just makes the whole thing a little more complicated. It doesn't really have an impact, but it's something you should be aware of to make sure that it's not affecting the governor conversion. So third example. This one is, at first glance, appears traditional. This is a plant also in California. This is a Voith mechanical system. Typically, the PRV will operate off of the shift ring or off of the servo motors, which means the PRV will not operate until the wicket gates operate. This system's a little different. The mechanical governor that was here before this was converted, and unfortunately you can't see it here, there's a hydraulic cylinder inside this box here that rotates this control point here. And as it goes to open and close the gates through the connecting linkages, operates the distributing valve. There is also a connection from here to the PRV dash pod. From a Penstock pressure standpoint, this is really cool because you can actually operate the PRV at the exact same time you were telling the gates to operate and reduce that window between when the gates close and the PRV opens. You reduce that window, you reduce that pressure rise that we saw earlier. The challenge we have here, though, is this system is 55, 60 years old. There is considerable friction in the dash pod linkage system on this job we experienced. And what that meant is that while the governor, normally you'd expect a small pilot cylinder to just be operating a dash pod, not have much force with it, you're now seeing some external device restricting your ability to control the gates because of maintenance issues with that. So there was no design change required to interface with this, but the PRV's operation, or maybe I should say the PRV's misoperation, negatively affected the ability to control the gates. We ended up going back and doing a bit of maintenance, greasing, cleaning up the fittings, cleaning up bearings, and actually replacing the control cylinder to get a tighter control on it. But much more than was originally anticipated when this was first understood just to be a standard PRV arrangement. So I'm going to go to the fourth example and the most complicated. This is in Oregon. This is a Woodward PRV control system. This is actually the first like this that we've seen. It's a unique system where the governor is essentially controlling the Howell-Bunger PRV bypass valve. In theory, it should work beautifully, but because of the complicated control mechanisms we'll show you on the next slide, maintenance was quite difficult, and if maintenance is difficult, it doesn't always happen. If it doesn't happen, then reliable system becomes unreliable. And this plant had some very, I should say unique, but had very low tolerance, risk tolerance for failure of the PRV, either to not open or to open too far. So there were absolutely serious concerns about changing any of this, but through failure mode effects analysis, we worked through replacement. So that's kind of the heart of what I want to talk about. For the second part of this is Here is a drawing showing the control system. Again, I'm not going to go into great detail on this, but on the left in blue is a traditional woodwork mechanical cabinet controller. And then on the right in green is a series of mechanical dashpots and linkages which operate a relay valve which controls the servomotor. So anytime you're changing control equipment, especially if you're changing control equipment from a mechanical system to an electrical system, whether it's on PRV controls, on overspeed controls, on cam switches to relay for wicket gate position for breaker tripping. Every time you're changing controls from one type of technology to another, you're going to have different failure modes. And those failure modes have to be understood. Usually they're acceptable, and you can put relays in fail-safe configurations and decide whether you need an open closed contact or an open contact. But sometimes it does get more complicated than just that. And that's what we were looking at here, where you had a little bit of a hesitancy to touch the system because you had a known and designed failure modes, and now we're looking at new failure modes. So we went through a rather thorough FMEA on this. We identified what the possible critical failure modes were, namely unacceptable penstock pressure rise caused by the failure of the PRV to open. That was primarily mitigated through a wicket gate rate limiter, so that if the PRV failed to open, the wicket gates would close slowly. That would result in an overspeed, more than normal, but that was acceptable. If the PRV failed to open and the wicket gates closed slowly, that would be unacceptable. The second unacceptable critical failure would be excessive opening of the PRV. If the PRV were to go full open due to a lack of control, that would cause unacceptable vibration in the plant. So we went through an FMEA. That process looks like defining the proper operation of what the critical failure modes are, identifying the failure modes of all of the new and existing equipment, identifying the failure modes of the system at large, power supplies, oil supplies, very important and often missed human failure modes, human misoperation, and then looking at single and doubly independent failures. We did not look at triple independent failures, failures of 3 independent pieces of equipment due to statistical insignificance, but it is important to recognize single failure modes that might cause multiple pieces of equipment to fail. And then, so what this looks like is you go through and you rank all these possible failures on detectability, severity, and occurrence, and then rank them. And we did this in 2 phases. We did this at the beginning of the project to come up with our initial design, and then on the final design to validate it. So based on time, I'm going to go through this a little quickly, but we rank every failure mode on detectability from it's almost certain that it's going to happen all the way through. It's incredibly unlikely that it could. Oh, sorry. This is detectability. That it's almost certain that you'll be able to detect that the failure mode occurred. The failure occurred too. It's going to be impossible to detect that this failure mode occurred. Severity, that there's going to be no effect of the failure all the way through. It's a hazardous condition to human life or equipment. And occurrence, it's almost inevitable that this will occur, or it's incredibly unlikely that this will occur. Through those, we evaluated 11 component failure modes and found 1 critical failure, 4 system failure modes and found 1 critical failure, and over 250 combinations of doubly independent failure modes and found 4 critical failures. Out of those, each was assigned a risk priority number, which is a product of the 3 factors we just looked at, and then 2 of those far exceeded the others by a factor of about 100, and those were the ones that were addressed. And there was a double failure chance of the PRV opening and the rate limiter not opening, so we implemented some additional redundancy in the control valving on the wicket gate closing, rate limiter, and PRV closing into 1 out of 2 redundant configurations. And there was a possibility of a total loss of control oil through operation of the duplex filter system. So it's not that uncommon for a duplex filter system to have ball valves on both sides of each filter. Sometimes it's actually required for lotto procedures to positively isolate a filter. But what that can happen is that you can fully isolate the supply pressure if you're not operating those valves right. So we replaced that valve with a simple 3-way valve with a, for lack of a better term, a make before break kind of arrangement where you had flow through both filters as you transition. And short of an operator actually closing a main gate valve, reduce the risk considerably of inadvertently shutting off that supply of oil. So finally, recommendations from this are pretty straightforward. Anytime you have a PRV on a system, you should do some level of analysis during the scoping phase to see if it's going to be impacted by the governor control. Understand how the PRV operates and if it will be impacted by the governor. Understand how PRV operation, this operation, will affect you and will affect the governor's operations. Understand the risks of PRV misoperation and the risks of slow gate closure if the PRV fails to operate. And then if those failure modes are changing or if those risks are present, then to do an FMEA is kind of the standard way to address that. And with that, open up time for questions.
Any questions from Matt?